hope you can see. Okay, yeah, thank you very much for the invitation to give a webinar in this network. I was told that there is mostly quantum fluid and superfluid condensed matter audience. I myself have worked in condensed matter as well in the past, so I have sympathy. But as my host explained, I was sort of shifting into astrophysical cosmology and astrophysics. And today I'm going to talk about a particular model for dark matter, which has a lot of characteristics similar to quantum fluids, Bose-Einstein condensates in particular. So since this is a dark matter candidate and this is a non-astronomy community, I can't help but point out a few things, how much evidence we have that there is dark matter in the universe. It's been now one of the longest standing open problems in science. It's getting 90 years or so that this is an open problem. It's longer than the ether in the 19th century. So starting with Fritz Zwicky in the 1930s, who realized that the luminous matter in galaxy clusters can't be enough to hold them up gravitationally. So there ought to be some form of matter which we don't see. And indeed, if you study galaxy clusters today, we can see them not only in the optical, but also in the X-rays, and we can decipher that there's more mass there that we can see, and we can calculate the equilibrium properties, and there ought to be dark matter. Then things moved on. People weren't too much bothered about it, but then in the 70s, when people tried to model galaxy formation, galaxy disks, galaxy properties in general, they realized that it turns out that you cannot produce galaxies within the age of the universe, say, if there's not dark matter around. And then, of course, famously, the rotation curves of spiral galaxies, also around the 60s, 70s, 80s. The fact that when you observe rotation curves in galaxies, here's a plot as an example, the velocity, kind of like a circular velocity plotted as a function of the radius from the center out to the outskirts of the galaxy. And you look how the stars move, no? You can measure it, you can determine a rotation curve. But it turns out if you add up all the luminous matter, the gas, the stars, etc., the curve you would get would not go through the data points. So you have to add another component, which is the so-called dark matter. And then it fits much better with the data. Also in the 80s, when the first large-scale galaxy surveys were coming forward, it was seen that galaxies are distributed in the cosmos according to a certain pattern, which is called the cosmic web. And here you can see in the right-hand side a simulation of such a thing. On the left-hand panel, this is actually an observation of galaxy survey. And galaxies are distributed on a very large scales, sort of like on filaments, and you get this web-like structure on large scales. And again, simulations have confirmed that you cannot get this within the age of the universe if you don't have enough dark matter along with it. And the form of this structure also depends on the nature of the dark matter. We'll say more about that. Yeah, that's already a slide to this effect. So why do we think dark matter should be cold, by which we mean non-relativistic? non-realistically moving. So its speed is very low, because we see in the large-scale structure that there is there's a lot of small-scale structure. And if your dark matter would behave relativistically or too long relativistically, you would smear out structures on small scales, but also on large scales. So for example, the hot dark matter paradigm, where people were thinking maybe the neutrino, if it has a mass, which was not known in the 80s, but supposed, could be the missing dark matter. And if people would do simulations, they would see that structures are smeared out, and you would not produce as many galaxies or small dwarf galaxies as you would as we observe. So we have good indication that the dark matter, whatever it is, should be non-relativistic. Then in the 90s, 80s, 90s, but then around the 2000s, we have two independent constraints, one from Big Bang nuclear synthesis and the other from the cosmic microwave background, that the missing dark matter cannot be baryonic, meaning it cannot be made of, some dim objects like very low mass stars, dim sort of compact stellar objects, which sort of sum up to make the dark matter in the universe. It has to be non-baryonic. And that means it is actually not part of the standard model. And since this has been around for a while, people have looked for candidates for the dark matter by devising sort of models beyond the standard model of particle physics. Another hint, which is a more recent thing, was the observation that when you do gravitational lensing of galaxies, distant galaxies, using foreground clusters, of course, when you do this and apply general relativity and all that, you will see that it works out well if you assume that there's dark matter. And similar, the characteristics of galaxy clusters, for example, this big picture up here is two colliding galaxy clusters sort of going through each other. And what you can see here, the blue things is sort of a map, a gravitational lensing map, which is a measure of the total mass of the clusters. The bright spots are the galaxies in the optical, if you want, and this purple color is the gas in the cluster. We know there's a lot of cluster gas, and the gas experiences shocks and deceleration when clusters collide and want to move through, while the other parts, the galaxies and the dark matter, doesn't feel so much of it. But the fact that most of the total mass is overlaid on top of where the optical galaxies are tells us that the dark matter is actually there and behaves in a similar way, that it's almost collisionless like the galaxies. So some have said this is sort of like an empirical proof for dark matter, if not for any detection, which is still missing. But yeah, which brings me to the actual candidates. And you said you can read the titles of the slides, because I can't, I hope. So the favored CDM cold dark matter candidates have been around for 40 years or more. There are two types. One is the idea that there should be stable supersymmetry partners of the standard model particles, and they are looked for in colliders and in direct detection experiments. And they are heavier than the proton, or even much heavier than the proton, and are thermal relics, meaning they're freezing out in the early universe, and then there's some abundance left, and this abundance gives you the dark matter, which we observe. The other proposal is the QCD axiom. QCD stands for the quantum chromodynamics. So that has been introduced to explain charge parity problem of the strong interaction as a means of dynamically resolving the fact that there's a symmetry issue. And this candidate is very much lighter. It's supposed to be 10 to the minus 6 to 10 to the minus 5 electron volt, but it's born cold, meaning it behaves like cold dark matter. It's not a relativistic particle. And just to contrast this, you know, the neutrino, right? We are sort of thinking that the neutrino has a mass is around 0.1 eV. So these are many orders of magnitude below, and it will get worse during this talk. So these candidates are sought for in detection experiments indirectly, directly, and have not been found yet. But this is a problem for any dark matter candidate. So what to say about the standard CDM model? It has big successes in the sense that from a dynamical perspective, if you model it, if you simulate structure formation, you can reproduce the large-scale structure, the cosmic web, in a good way. It's really fantastically close. Also, density profiles, rotation curves of galaxies and clusters, as I mentioned in the beginning, can be reproduced very well. And the overall bottom-up hierarchical structure formation paradigm, where small objects in gravitational equilibrium form first, and those merge to form even bigger structures, seems to fit well with observations. However, there are also the failures, and these failures have been also around now for 20 years or so. And they refer mostly to scales which cosmologists call small scales. These are scales are smaller than typical galaxies, roughly a kiloparsec or 10. And just to give you, a kiloparsec is roughly a bit more than 3,000 light years across, right? So these are the small scales, but they're small in term compared to cosmological scales. The fact here is that the standard CDM model predicts a lot of structure and substructure on all scales, really down to small scales of Earth mass size. But we do not see this substructure. It has not been seen in microlensing detections within the Milky Way. And also, this model predicts a lot of structure of relatively large subhalos, so gravitationally bound subhalos, which are large enough that they should host luminous galaxies. And we haven't seen as many. So there are dwarf galaxies around, and we keep finding more. But the issue is there should be so much structure which also hold galaxies in it. Why aren't we enshrouded with hundreds or hundreds of dwarf galaxies around the Milky Way, say? And then in the innermost parts of the rotation curves, so I showed you an example previously, there are actually deviations to the CDM model between data and predictions. And these deviations refer to just to the dark matter dominated dwarf galaxies. So this seems, unexpected, because the dark matter dominated dwarf galaxies should be best modeled by the dark matter model. And yet here we find discrepancies between what the data points suggest and what the models want. And of course, we have no direct or indirect particle detection yet, but this again refers to any dark matter candidate. So these issues, especially with the small scale problems which astrophysicists are interested in, has led to a revival of non-standard CDM candidates, especially those who do not form structures excessively on small scales. And there are several candidates, and one big family is this so-called Bose-Einstein condensed dark matter, which is a huge family actually. And I'm focusing on this in this talk. So just to say that even this literature is not a new one. It has been also around for decades. One way or the other, these things keep coming and then going, fading out of favor and then coming back, it seems. But anyway, since the 2010, there has been an enormous explosion in literature on this kind of dark matter model, in the astrophysics literature especially, for all its dynamical differences to the CDM model, as I hope I can convey today. So yeah, there's a zoo, a family of Bose-Einstein dark matter or scalar field dark matters, it's also often called. There are a lot of names, and I should say, maybe you had expected I would tell you a lot where they come from. I will not, because I'm not a particle theorist. I can only tell you that candidates usually arise from string theories or some other extra-dimensional theories, which predict bosons at various mass scales, especially at very small masses. And so there are models, particle theory models where these candidates come from. But I will not talk about this branch. I will talk about the dynamical aspects. And if you have heard or seen talks where people talk about fuzzy dark matter, quantum wave dark matter, and BEC dark matter, and whatnot, ultralight axions, they're all belonging to this big family. The difference is just, is there self-interaction included or not? Is the mass of the boson similar to the QCD axion, 10 to the minus 6 eV, or is it even lower, etc.? Things like this. And yeah, as already indicated, we are actually interested in very, very ultralight bosons. So we're talking about masses in the range of roughly 10 to the minus 23 eV. And as I already said, I will show the equations shortly. This model assumes that we have, say, a species of spin zero bosons, which, for whatever reason, are in the same state, maybe by way of a Bose-Einstein condensation in the early universe. And then you can describe them with a kind of order parameter description. Yeah, these are these kind of slides where you are very familiar with anyway. So the idea is similar than in the lab. The fact is that these ultralight bosons can fulfill the phase-space condition for BC very easily, because their mass is so terribly small that the phase-space condition is fulfilled in halos and even in the usual homogeneous universe background, say. And as I already said, you might, similar than you're used to, think of it as a kind of effective field description, where you model this whole thing with one field, and it's like the order parameter of the condensate. And this brings me finally to some equations of motions, which in this setting here, when we talk about individual galactic halos, right, we want to model a halo of a galaxy or a galaxy cluster, assuming this kind of dark matter, we can model it using these equations of motion. And as you can see, this is a nonlinear Schrödinger equation or Crosby-Debski equation, as you know it well, with or without a self-interaction term included. The important difference to the lab is, instead of a magneto-optical trap, your trap is the gravitational potential. So the idea is that this dark matter halo has self-gravity, so it creates its own gravitational potential, which means there's also a Poisson equation if you're in the Newtonian regime, which we are in this talk. And then you have sort of a set of equations, the Crosby-Debski equation, along with the Poisson equation, which couples the mass density, which is related to the amplitude squared of the wave function psi, here with the Crosby-Yancey equation. And you can already imagine that this makes it a bit harder to model also. No? It is a nonlinear set of differential equations because of the coupling here to the Poisson equation. So what happens is that in most of the literature, people in the astrophysics literature, people disregard the self-interaction because it adds a complication to an already complicated system of differential equations, so to speak. But I will also show results including self-interaction because it makes things interesting, as we know from the lab, actually. Right, and this, yeah, but the part, what is similar than in the lab is the fact that this gravitational potential doesn't feel, how should I say, this gravitational potential describes density gradients on relatively large scales. It doesn't feel the sort of the length scale of the self-interaction, which is also assumed to be short range, similar to the lab. So this is this slide, things which you know well, not the fact that there are certain assumptions when you write down a Gross-Brzezinski equation. You have a diluteless condition, etc., and you have the fact that you model this, at least in this setting, model this self-interaction like a contact self-interaction, as you are familiar with in the lab. Yeah. Also, what you might, will be familiar with is the fact that we rewrite these equations conveniently in terms of so-called quantum hydrodynamic equations by introducing this polar decomposition of the wave function, right? We write it as amplitude and phase, and then we can define a number density, probability number density, which is related to the mass density, or the psi is related to the rho. And also the velocity is defined as the gradient of the phase. You can see these equations because I can't quite. Is that correct?
Yes, we can.
Okay, super. Good, thanks. So why do we do this? Well, astrophysicists normally don't work with wave functions. Normally, they like to have hydrodynamical variables. So they are used to thinking in mass density, velocity, and pressure terms. That's what you see here. So you have an Euler-like equation, and on the right-hand side, you have the pressure terms. Of course, in astrophysics, we have the term due to the self-gravity, phi here, gradient of phi. And the pressure terms for BC dark matter, of course, are characteristic for BC dark matter, namely the quantum pressure. And if you have a self-interaction, then a self-interaction pressure. But this is now the upshot. Because you have these pressures, you have at least the quantum pressure, even if you disregard self-interaction. It will make sure that your system cannot excessively cluster in a sense. There's always the smallest length scale given by the de Broglie wavelength, below which you will suppress structure formation. And that's the thing which is interesting and which makes it a possible resolution to the small scale problems of the standard CDM model. Yeah, again, this sounds like a summary slide. I mean, I have a lot of slides which I will skip, so I might as well say a few things already. You can imagine that with this different set of equations compared to the standard model, which is a sort of collisionless n-body, if you want, collisionless Boltzmann equation type of description, that this model will give you different phenomena. And this phenomena can be looked for, searched for, and possibly found or constrained at least. And I will mention a few as we move forward here. Yeah, as I already said, I already indicated that the de Broglie wavelength, if you have no self-interaction, the de Broglie wavelength is at least the length scale, which is the most basic in a sense. And what is the smallest allowed or largest allowed de Broglie scale? That depends on the structure you want to have, right? If we would say if we would say, oh, we are happy with Milky Way galaxies, which have 10 to the 12 solar masses and they have a size of roughly 100 kiloparsec, so the Broglie wavelength would be roughly 10 to the minus 25 eV. So you see where these small numbers come from. They might be predicted from some string theory, but then astrophysics, oh, wait a minute, if I can suppress structure below a certain scale, that can help to resolve my small scale problems. But of course, we have to observe the fact that we do see smaller galaxies than the Milky Way. But what are the smallest galaxies? Astronomers keep finding ever smaller ones over the years. So, but let's say roughly a few hundred parsecs or a kiloparsec diameter across, say, of a galaxy gives you the Broglie of roughly 10 to the minus 22 eV. So this is sort of a fiducial number you will see in other slides and plots and papers and talks which people present, because this is sort of the smallest scale by which we will not wipe out structure below a dwarf galaxy size. We want to keep them, of course. And yes, so this gives you a rough number. And then the issue is, what about the other regimes, like in the lab, right? In the lab, we are used to saying, okay, we could have an ideal Bose gas or whatever, and then we have a case where there is a strong self-interaction, repulsive one, this famous Thomas Fermi regime. And this is also the case in this setting. We can think of a regime where the self-interaction is strong and repulsive, and there's another length scale, the Thomas Fermi radius. And that is much larger than the Broglie scale, same in the lab. No? But here, the difference here is that we have a system under self-gravity. So if you calculate hydrostatic equilibrium with the gravity term in it, you get a Thomas Fermi radius, which of course has the gravitational constant in it, for example, right? And not only the self-interaction strength. No? So that comes from a hydrostatic calculation. And it turns out that in this regime, there's even an analytic solution. And it relates to n=1 polytropes, which are known from the literature since ages. So one can, calculate that and plot profiles. Just as an example, the upshot is that in each case, in each limit, the limit without self-interaction and the limit with a strong repulsive Thomas Fermi limit, you have sort of constant density cores. No? You have no so-called cusp, because the standard model, CDM standard model, predicts cuspy densities, and BEC-dark matter predicts flat cores, so finite density cores. Again, because of the quantum pressure, right? Or the self-interaction pressure, but that's the reason. So a note on nomenclature. I mean, you hear these things, solitons, and here already I said it, these finite density cores, solitons. Astrophysicists mean something particularly which may not be what you have in mind. So solitons in this context mean self-gravitating objects as ground state solutions of the Gross-Pitevsky-Poisson equations in hydrostatic equilibrium or close to it, which means these objects are sort of stable against gravitational collapse by way of quantum pressure, if there's no self-interaction, or by way of this repulsive self-interaction pressure, for example, in this Thomas Fermi regime. The intermediate regime is harder to study, is always not the case, sort of where you have a weak or intermediate self-interaction. Why solitons? Well, they call it solitons because it's sort of a persistent object, right? It doesn't fade away. It's like a wave packet confined to a Newtonian gravitational potential. Its own gravity holds it up and inhibits dispersion. That's why they call it solitons. And to add to the confusion, sometimes these solitons are also called boson stars, which are actually originally something else. which are sort of the general relativistic brethren of the Bose-Einstein condensed self-gravitating objects under Newtonian gravity. If you go to the regime of strong gravity, you get to boson stars. But anyway, I will not talk about them today. So, boy, this is hard to see. Now, what happens with these single solitons, right? If you model them and simulate them, as you can imagine, since there's this quantum pressure, they will not be totally stationary in a sense. No? There is this, they can sit at rest, so there's no net velocity, but their tail sort of oscillates and keeps oscillating over Hubble time and longer than a Hubble time. Hubble time means roughly the age of the universe. And people have known this, people have modeled this, and the question is what does this mean for the model? If you add a self-interaction, it turns out that these oscillations are small in amplitude, but one must also bear in mind that the repulsive self-interaction opposes gravity also. So you have now quantum pressure and self-interaction pressure, which opposes gravity. So you could get into a regime where your soliton or your Bose-Einstein condensed dark matter object sort of smears out or wants to spreads out after all, and is not bound gravitationally anymore. So there are these dynamical competition between gravity and quantum pressure, and gravity and quantum pressure and self-interaction pressure, if it's included. So this is the astronomy side, but of course, in the condensed matter side, as you all know better than I do, people have considered possibility of mimicking one of our interactions in the lab, no, by thinking of specific laser configurations to induce a gravity-like interaction between atoms, say. And this has been studied also more than 20 years ago. And here, this diagram from this paper is just as a reminder that these things have been also around in the lab context. On the left, on the y-axis, you see sort of a dimensionless self-interaction coupling strength, and on the x-axis, you see a dimensionless gravity strength, a coupling constant. And of course, if all the gravity or self-interacting coupling constants are small, you are in an ideal regime, no, where you have the interacting Bose gas. If your self-interaction gets very high, no, repulsive high, you get in the ordinary Thomas Fermi regime. And then there are other regimes where you have this gravity-like term taking over here, or a regime where sort of gravity opposes the self-interaction term in specific ways. So people have thought about mimicking one of our interactions using lab systems, lab BECs under certain configurations, under certain traps, so to speak. Yeah, this is an example of when we get back to the soliton issues. Of course, the solitons mean that the density in the central parts of halo, say, is finite and almost constant, but it could still be sorry, I'm getting a call, even so I thought I should not, I'm not gonna. You might still compare this with galactic data. So for example, here is a plot of slightly average mass profile in the Milky Way. Here's a radial distance on the x-axis, and the y-axis is solar mass. And here you see data points of various central galactic objects. And these shaded areas give you sort of solitons with bosons of a certain mass. No? This sort of light gray is 10 to the minus 19 eV, and this blue is 10 to the minus 22 eV. So depending on the boson mass, your solitonic core sort of will be more pronounced or less pronounced. And you may compare this with actual data, say. And then you could say, okay, maybe this or that model is disfavored because the central parts are too compact, say, or the other way around, it's too extended. And so one can use data and compare it with models and really try to see whether there is a parameter space which can explain data. And there is still a parameter space left. I should say, since most of the literature focuses on models without self-interaction, they have one free parameter, which is the boson mass. So there's only so much you can play with that. No? If there's self-interaction included, then of course you have another parameter. And then you can also have models with higher boson mass because your self-interaction parameter now helps you also to be in accordance with data, say. Yeah, and just to say that for years now, people have looked at this. This is not a new thing also. People have tried to model galactic velocity rotation curves with this model and sort of say, okay, for example, in this regime of strong self-interaction, your Thomas Fermi radius of your central solitonic core should be, say, something around 2 kiloparsec, for example. So this has been done, just to give you examples. But again, as I showed you in the beginning, we expect a lot of different structure in the universe. We expect the cosmic web, filaments, etc. So we cannot just live with these solitons, which are the result of hydrostatic equilibrium. We have to have something else. And the idea is, well, as in the standard CDM model, small objects might just merge. No? They attract each other by gravity. No? They merge into larger ones and eventually form bigger galaxies and the cosmic web, etc. And people have looked at that and have done simulations where they take some of these so-called solitons, sort of ground state solutions of the Gauss-Poisson equation, and smash them together, right? Let them merge and see what comes out. And normally you should do this in an expanding background because we live in an expanding universe. But people have also looked at static background because it's easier computationally. Usually these calculations are very computationally expensive because it comes down to the fact that you should be able to resolve the de Broglie wavelength, say kiloparsec, in a cosmological simulation which has a length scale of a megaparsec or 100 megaparsec or so, right? So this is something which is computationally prohibitive. And so people have done various scenarios where they have to either make an easier simulation without expanding background, or do an expanding background, but sort of calculate a fraction of the cosmic evolution and not to the present, things like that, compromises. So what happens if you smash together this kind of ground state solitons and have them merge? Well, what happens, generally speaking, and people have known this also for some time, what happens is that in the center of this final object, you will again see something like a solitonic halo core, which is more or less structureless, really like this kind of uniform, almost uniform core. but it is enshrouded by highly dynamical halo envelope, and that envelope does not fully relax. You can calculate for Hubble time. Here's an example, 14 giga-years, say, and you have these sort of wiggles out there in the outskirts, or you calculate it for 10 times the Hubble time, say, and you still get the wiggles and the oscillations in the outskirts of these halos. So these halos are very, dynamical. They do not really relax. And here is a more beautiful picture of a really sophisticated simulation, but also here without an expanding background, but nevertheless, suppose you have these solitons, which are Gaussian peaks often, or some model for it, and you smash them together. And what happens is they form a bigger structure, of course. And in the center, you have this higher density central soliton enshrouded by this envelope, which is very much dynamical. And the idea is that if dark matter is BEC dark matter, you start out with smaller blobs, like small galaxies, say, they would come together, merge, and build bigger halos as a result, like this one in the right bottom panel here. And turns out this halo envelope shows signs of quantum turbulence. If I get to it, I can say more about it. And this is also an example of how it looks like. There's a CDM model on the top and a Bose-Einstein dark matter on the bottom. You can see you evolve the universe, say, from early epoch of a higher redshift down to a sort of more recent epoch, not the present, but more recent. You can see how from a uniform, almost uniform background structure rises, structures form, filaments form, halos form, bigger halos form, smaller halos are in between here, and you have filaments. A lot of structure in the CDM model, and in the BEC dark matter model, you have less structure, again, depending on parameters, of course. But in principle, you also form filaments and all this. And depending on the parameters, you might form more or less structure. This is then a subject of observation, right? Which models will fit observations and which won't. Here is sort of a zoom in of how such a filament looks like. In the CDM case, right, you have a big halo and you have smaller subhalos here and sort of filamentary structures in between. And for Bose-Einstein condensed dark matter, you have also kind of like a bigger halo, which is the result of a lot of merging, and you have this interference patterns here, and you have interference even along the filaments. And that's what people have seen in the simulations. So of course you could say, well, of course, if I have a wave equation now for my dark matter, I will see wave interference phenomenon. No surprise. Sure enough, the question is, can we disentangle what would be just a classic wave phenomenon from an inherent quantum wave phenomenon, say? And there is this whole topic of vorticity in Bose-Einstein condensed dark matter, and the question whether quantum vortices can arise and even quantum turbulence. And like in the laboratory, there are at least two routes to vorticity. We have either net angular momentum, that is, we spin up the condensate in attempts to form a vortex, right, or more than one vortex, or via mergers of solitons, as I already said, the idea that in structure formation you have a merging of solitons, even if you have no net angular momentum in your system. And even this is something I vaguely remember to have seen a paper in the lab where people would smash together, or it's simulation, smash together three BECs and sort of find vortices in them. So rotation or mergers lead to two things. First, it leads to non-spherical halo shapes, and often also to quantum vortices and quantum turbulence. Generically, I would say quantum turbulence, at least, seems to be really, often appearing. And I have to watch the clock, but just briefly a reminder that, of course, a non-vanishing angular momentum does not necessarily mean that you have vortices already. Of course, you can still have a case here. You have, for example, angular momentum plotted as a function of angular velocity. You can have a case where your angular velocity is finite, no? You're spinning up things. You have a finite angular momentum, but you do not have a vortex in the system. Only as of a critical angular velocity, you form the vortex. And what happens instead is that your system has a non-spherical shape. No? And a similar thing in this BC dark matter business, so to speak. And what would be the spin in our setting? Well, if structures form, and we know there's always angular momentum in astronomy, we always have some torque which can impart an angular momentum, a spin onto an object. So we know from CDM simulations, structure formation simulations, and also observations indicate that halos, galactic halos, should have a net angular momentum, but they're not rotationally supported. This is kind of the spin parameter which describes the ratio between rotational and gravitational potential energy. They're not rotationally supported, but they have a net angular momentum. So this is a reasonable thing, even in the standard model. So why not for the BC dark matter? So could quantum vortices form? And people have looked at that. First, yeah, this is something which I usually show for people who are not familiar with this, but you are all familiar with that, so you can skip it, just to remind us that in a vortex, the density drops. And also you have a circulation condition, which is quantized. And vortices locally break the rotationality constraint. Because this is the same. And here, again, the vortex lattice from the lab, the famous pictures. So people have looked at that, and basically two things happen. First, because of the irrotationality constraint, this will lead to predictions what your non-spherical halo shape should look like. And it turns out, if you look into it more carefully, you can find models, even analytical models, to describe this, which have been known in the stellar astronomy community for a while, funny enough. For example, here you can see that rotating BC dark matter halo cores can be modeled by irrotational Riemann-S ellipsoids. So they are really irrotational, have no quantum vortices, but this is a prediction for the halo shape, which is different from the standard model, say, because you wouldn't expect such a shape, no? Because you have no irrotational constraint in the standard model, standard CDM model. Also, what can be shown that if angular momentum is high enough, reasonable numbers, which you would expect from the standard model as well, you can form quantum vortices in Bose-Einstein condensed dark matter. However, only if you have self-interaction. And in fact, if you're in the Thomas Fermi regime, parameter space of favored vortex formation overlaps to a great extent with your Thomas Fermi parameter space. So even this is not too surprising. This is something we know from the lab. No? We have much more vortices in the Thomas Fermi regime than if you are not in the Thomas Fermi regime. And in fact, we could show also then in the regime without self-interaction, you do not expect a quantum vortex in the center due to angular momentum. They can only arise from other means, for example, merging or things like that. Yeah, so these are things which you can study, right? You can do a calculation and you can try to be analytical as much as possible. But I already said in words what I can skip a few slides. It's just to show what the shapes for here, the Riemann-S ellipsoid could look like. And so what is this from angular momentum is possible if you have a high enough self-interaction. Otherwise, it's not favored. This is one form of vortices, but now, sorry that I'm skipping all this because I'm running out of time. There is this other effect of quantum turbulence, which I really want to get to. That's why I skip so many slides. So the same paper where I showed you the picture before, where the solitons merge into this bigger thing in the end, they have looked into details and have seen that in the envelopes, these wobbly envelopes, they do see vortices, they do see vortex tangles reconnecting, etc. So they really do see signs in a scaling which is similar to what people have seen in the lab or are predicted for the lab. And these vortices do not arise from angular momentum necessarily, but from the sort of the highly dynamical merging process. And you see this even in a smaller case. So this was a 1 megaparsec box sophisticated simulation. Even in a smaller setting, you see it. For example, here these people they smash together a few solitons. You see a density profile on the left, and you can sort of look into it in more detail and see vortex rings and vortex tangles and so on, even in this case. But the point is these vortices in the envelope, their self-gravity seems to be negligible compared to the vortices in the central parts. And so they have different properties, and possible detection strategies are also different as a result. And yeah, so, right. So let me get to a final slide. So Bose-Einstein condensed dark matter is interesting. There are several motivations. First, from the astronomy side, there are issues with the standard cold dark matter model, which have not been resolved, even so they are also now 20 years around. So alternative candidates are being studied, and BEC dark matter is an interesting candidate. Then prominent particle theories generically predict ultralight bosons. I haven't talked about that at all, in a sense, just flashed it to you, but you have to believe me that there are also particle models which predict them. The astrodynamical signature effects distinguish it clearly from CDM predictions. We might have quantum phenomena on galactic scales, meaning we might have vortices of sizes, hundreds of parsecs across, or a kiloparsec, vortices in the centers, if BEC dark matter has a self-interaction. And we can investigate physical regimes which are unattainable in the lab, in a sense, as in the astrophysical simulation setting, because we study them under weak or strong self-gravity and compare it to galactic data, say. And also, this later point is interesting because we can try to understand classical and quantum dynamics in a gravity environment. I couldn't get into it because time runs out, but one can even understand the emergence of these envelopes, of these halos when solitons merge together. This kind of classical dynamics emerges naturally from the quantum dynamics on the scales of the Broglie scale, because it can be shown that there is an effective large-scale pressure, which is similar to velocity dispersion pressure, which really stems from the quantum pressure. And so there's no need to ask where's the transition between quantum and classical. It's an ill-posed question almost. You can see it sort of in the dynamics playing out, that on a statistical sense, the classical dynamic emerges out of the quantum dynamics, which acts on smaller scales. Okay, yeah, so I hope I'm not overrunning time, and I thank you very much for your attention.
Oh, thank you very much for a brilliant presentation. I didn't want to interrupt this because it was so interesting. I can see that some people have already had to go elsewhere. So before we continue with questions, I will say that the next presentation will be in January. You will receive emails about that, and it will be posted on our website probably after Christmas. And do we have any questions? I think Jonathan was the first one.
Yeah, thank you very much for very interesting talk. I just had a question about the last point you raised about quantum turbulence. So the Gross-Pityevsky boson equation, even so, if it's in the fuzzy regime, there's no self-interactions. I recognize this this figure, and if I'm not wrong, this was done using a pseudospectral technique. Now,
yes, this Moch et al. 2017, yes.
yeah, it's definitely MOX, yeah. In order to do a pseudospectral technique, you have to use some kind of what's it called, gene swindle, where you subtract off the mean density in order to make the well, it's not Poisson equation, it's more like a Helmholtz equation, well posed. But then the subtracting off the mean density is an effective self-interaction term, which is attractive. Is it not? I'm not sure. I'm just trying to think this through. In which case, would you expect to see these quantum vortices? I mean, quantum vortices, to my mind, is only when it's a self-repulsion term. I don't know if you can comment on that.
Yes, right. I know what you mean with this subtraction and the Poisson equation. People tell me that is fine. This is just a technical thing. Yes, I agree with you that my thinking always has been that you have vortices once you have a self-interaction included, and you don't have them when you don't have a self-interaction. And that's what we see when we study the angular momentum problem. Then we see that neither the necessary nor the sufficient condition is given for a vortex to arise in the fuzzy dark matter. However, now people come along with these simulations, right? And they show this highly dynamic envelope. Yeah, what can I say? It's a good point that you raised, that there is some, that there might be some hidden self-interaction somehow in the way that the equations are solved. I should look into this.
And it may be something to do with, I know there's this famous paper, I can't remember the name of, like, is the gene swindle, resolving the gene swindle, and then you actually end up with a Helmholtz equation, which, you can interpret as some kind of self-interaction, but maybe that's the answer, maybe not, I'm not entirely sure.
I mean, I should look, because people have also used other techniques, for example, using SPH, also the smooth particle hydrodynamics methods, not the pseudospectral methods.
Yeah,
I do not remember now what they have found in their halo envelopes.
I wonder, those smooth particle hydrodynamics, I really will worry about something small scale like a vortex core, but this is just a personal bias.
Yeah, they may not be able to resolve it. That's right. Yeah, and we have, I mean, we had done some sort of proof of principle simulation in a Thomas Fermi regime, where we would sort of do such a structure formation simulation, and it would look, it would also look similar in terms of the filaments you see. But we haven't analyzed it in terms of whether vortices could be hidden in this kind of structures. We should look at it, actually, because there we would expect them in any case.
Yeah,
that's an interesting point. Yeah, thank you.
Okay. Oh, thanks anyway for a great talk.
All right, thank you. I think Toshiki Kanai was the next one.
Can you hear me?
Yes.
Okay, so yeah, thank you for the good talk. That's interesting, and also thank you for sharing the beautiful results. So I have some questions about Soliton. You may know the Solitons may obtain dynamical instabilities and break into vortices in the standard BECs without no self-interactions. Did you observe such dynamical instabilities or vortices in the simulation?
Yeah, so I mean, the only thing I can point to right away is the fact that we did find that a vortex can arise in that soliton if you have high enough self-interaction.
Yeah.
In that sense, the soliton can break up in one vortex and possibly in several. But as I said, you need a high enough self-interaction to do it, and not in the fuzzy dark matter regime.
Did you include a finite temperature effect, or are
No.
you do you plan to include it later?
Yeah, no, there's no finite temperature here at all, because yeah, that's right. I mean, the idea is you're starting with this, you say, okay, all your particles on the ground, are in this sort of many particle ground state, and you model it with this order parameter, so to speak. You have your Gross-Pedievsky equation. As far as we only use this form of the Gross-Pedievsky equation, I haven't looked at temperature effects. There may be some papers around which try, but not so much in the astronomy literature.
Oh.
More in the condensed matter literature, right? That's my understanding. That
Yeah, but
modifications.
but I feel it's more natural to include a finite temperature effect or some temperature effect. But anyway, okay, I got it. And one more question. So in the galaxies, there are many kind of massive objects, or in a sense, kind of non-dark matter object, and those maybe serve a kind of impurities. And BEC has a wave property. So can we expect kind of localized effect or modulations of the dark matter in galaxies?
Yeah, your question refers to a whole branch which I haven't mentioned at all. You could argue that suppose you have some other halo object, right? Some stellar cluster, right? Or anything move through it, right? And what happens? And people have studied things like tidal effects, or how the tidal effects on stellar clusters or on stellar streams change if you assume this kind of dark matter which has superfluid characteristics, so that the tidal effects on your non-dark matter things like stellar clusters, whatever, are different than if you had the standard CDM model, where you do not have the same friction and all this. So I guess this goes into the direction you're saying, because in a sense, this would be like an impurity, right?
Yeah,
you have
yeah.
a globular cluster, right, in a galactic halo. The galactic
Mm-hmm.
halo is made of this BC dark matter, and so you have this globular cluster going through, and the way it's going through, or the way there is some tidal interactions also. Yeah, so that there are works to this effect, which I haven't mentioned. I have only mentioned a really tiny fraction of things, of results.
Yeah. Thank you for answering my questions.
Thank you. Gerasimus is the next one.
Yes, hello. Thank you very much for the very nice talk. We have a small, we have a relatively recent fuzzy dark matter group in Newcastle who have been very much influenced by your extensive work on this. So, I have two questions, if I may. First of all, how you mentioned this vortex network in halos. Do you have any sense of how this might be observed, given the low densities there? And my second question is, there are more and more reports of lighter and darker objects being found around, like satellites for the Milky Way. So do you think that eventually we will find these small halos that the CDM predicts and fuzzy dark matter is supposed, wave dark matter is supposed to resolve?
Mm-hmm. Okay, yeah, good questions. The issue of detection. So I guess actually this Hui et al. Paper talks a bit about this issue. How would one detect them? And I guess they propose to use microlensing as a possibility to detect vortices in the halo, so to speak, since they seem to be so ubiquitous in the halo. In a vortex, right, the density drops. So the issue, of course, depending on the size of these vortices, right, compared to whatever your field of view, and you have to have microlensing detection. There's not too much work on this. I think this paper is one of the few which talks about detection issues. also in the context of the QCD axion, because they say, okay, if it's the QCD axion, the effects are on a much smaller scale, right? Not so much on the galactic scales, but on smaller scales, but still they should be here the way. And the question is how to detect them. So microlensing seems to be one way to go, but probably very hard to do. And microlensing, just let me, you look at whatever stars in an external galaxy like Andromeda, whatever, or the Large Magnetic Cloud, and you sort of you look how foreground objects sort of move in front of it, and if you have and if you measure sort of dips in the light curves, this could sort of be a way to say whether there is some object in the line of sight between you and this stars that you observe. And this has traditionally been used to detect compact dark matter objects in the Milky Way, say, right? Microlensing. And so vortices in the envelope might be also detected by microlensing. With respect to your other question, it is true, people find ever smaller galaxies and more satellite galaxies also in the local group. That's fine, we will probably find more and more of them. And that's why people say, oh, maybe we have enough and there's no problem. I would still say we have a substructure problem. First of all, we do not see all the small substructure yet, which also CDM predicts within the Milky Way, say. And then the issue with the too big to fail, right, the subhalos. I mean, we do expect a lot of gravitationally bound subhalos, which are big enough, massive enough that they should host visible galaxies, and they don't. And I don't think this problem may not go away so easily, even so people say they can sort of deal with it. But...
Yes, I agree with you. Thank you very much.
All right, the next question is Justin.
Hi, this is Dan Sheehy filling in for Justin. We're watching from Louisiana together. It's been a great talk. Thank you. My question, I come from the field of BEC cold atomic gases, and I'm wondering, are there any experiments in a regular cold atomic gas BEC that would be relevant for the types of questions that are interesting to these self-gravitating cold dark matter BECs?
Yeah, that's actually a good question. A question I will throw back to this audience, I guess. I think there have been proposals, as the one case I showed in one of the slides, which sort of made a case how you might possibly make a configuration such that you mimic one of our self-interactions. The only thing I know is, I mean, people have studied molecular condensates, and there you may have inherent dipolar interactions. I'm not sure how much that system is close to the one I have in mind here. I also don't know whether some of the proposals have never been worked out experimentally. I mean, these are experimental proposals, but many of them are hard to execute. And I don't know, I would like to know myself, actually, what's the status on this in the lab. But I would imagine that for sure, this is something which is interesting from many perspectives, not just from condensed matter, but also from the similarities to the astrophysics models, etc. So I think this is something which would be could pay off if somebody. Yeah, does anybody know? I mean, if somebody knows who is still online, about what the status is in the lab.
I don't know, but if somebody does, please put your hand up. In the meanwhile, I have a couple of questions of my own, which I'd like to ask. There is a third route, or maybe this is what you were talking about, but I just didn't understand it, to vortex formation, which namely passing through the phase transition rapidly. It's called the Kibble-Zurek mechanism. Is this what happens in the collisions, and if not, then is it relevant to dark matter in any way?
Yeah, that's a good point. Yeah, of course, you're absolutely right. I would think if it does, it is only relevant. Well, it is relevant in the early universe, if so, right? If there is some era where, say, ultralight bosons go into this Bose-Einstein condensed state, and if there is some, yeah, I don't know what would have to happen in the background. Suppose that there is some, yeah, I can imagine that vortices could arise that way, but they would have been produced sort of in the early universe already, and would be around ever since, maybe. That's right. In that sense, what I'm talking here, well, of course you could say, okay, these things also happen early, but here it's sort of a result of the dynamics, in a sense, right? You start out, you merging things, and then vortices may arise, or things get a torque and then a vortex forms. This only happens when structure formation becomes nonlinear, in a sense, when gravity, when you move away from the nearly homogeneous background universe to the universe which forms linear perturbations, and then go into the nonlinear regime of structure formation. That's the kind of vortices I talked about, in a sense.
Yeah.
But your proposal, yeah, that's right. Those vortices would probably arise in the early universe, the very early universe.
Well, I
already.
mean, one might say that let's say you have a collision, and then there are some regions where density increases sufficiently that you actually undergo the Bose condensation phase transition, and then in that region you would get the Kibble-Zurich mechanism acting depending on the rate at which you're passing through the transition.
Mm-hmm. Yeah, good question. You will have to think how the density could change so quick, well, so dramatically in the early universe, right? But
Sure.
otherwise, why not?
Okay, well then I had another question, if you don't mind, which is that
Sure,
so
I'm happy to.
if in the lab we rotate let's say superfluid in like a really smooth container, then it may happen that the critical velocity for vortices to form in this container, which was, let's say, originally not rotating, and then when it's already in the superfluid state, we start rotating it. It may happen that the critical velocity is so high that vortices just never appear in a state where the energy considerations would give you a lot of vortices already. And so if you then imagine a kind of a gravity bound condensate which didn't have a container around it, so the wall is kind of perfectly smooth, if you like, or something, then this might also happen. Has anybody thought about that?
A good question. I mean, with respect to the QCD axion, some axion people have, Kiwi notably, thought about the idea that somehow vortices would arise, maybe for a few and then many, and they might maybe even coalesce to form a big vortex, sort of like the big vortex in the lab, right? Which sometimes can arise. Now, if you have higher angular velocity, then you end up with a big vortex in the annulus right around it or so. But these have only been sort of proposals or sort of back on the envelope calculations. One should look into this more carefully. I would like to see what comes out. I don't know what would happen. After all, you don't have the container, that's true, but you have your gravitational potential well, say, so to speak, and suppose nothing can escape. Maybe you can form a central big vortex as a result of high spinning or something.
Or then also you have impurities, which is all the regular matter that's also rotating.
Yeah, I mean, it would be a very strange halo, no? Because you had a sort of a density depletion, which is very pronounced and strong, right? And you have this sort of, yeah, the density is sort of pushed out to the outer skirts in a sense. But in principle, if it's a small halo, which is sort of, I don't know, tidally distorted by some bigger halo in its environment, who knows? But yeah, no, I don't think anybody has really calculated this. in a way
Well, I
that
mean,
is.
the reason why I'm saying is that obviously we in the lab we have lots of experiments that probe all sorts of questions, and we'd be very happy to help any people trying to apply these ideas to some other systems if we just can connect with them.
Mhm. Yeah,
Um,
definitely. And the lab is the way to go, because the colliders, we will. I mean, what I mean is not the condensed matter systems. There's a lot of things you can still study, while the high energy frontier is getting harder and harder. So,
Yeah.
but again, it brings me back to this point with the 1/r kind of interactions. If one can have them in the lab, that's always something of interest to astronomers too.
All right. I don't see any further questions, so I would like to thank our speaker for a brilliant presentation, and also all the participants for a long conversation, which was very interesting to follow.
Yeah, I thank you very much for your attention and for your interesting questions. And
Yes.
yeah, I wish you a nice holidays and a peaceful new year.
Yes, you too. And with that, I am going to close this webinar now. Thank you very much.